Hello, IB Physics. Ms. Getz here, and I am going to go over a few things in this Desmos template that I have created for you. When we're at school at Harding, we'll actually be using a software called Logger Pro that does some things that are a little bit more complicated and convenient than what we can do on Desmos, but Desmos is really excellent, and you have it on your iPads, and it works just the same on your computer. So I'm going to show you a few things with this template for our rubber band lab that you're going to be using. First thing that I want to point out is make sure you have signed in to Desmos. So my name is here because I've signed into my Desmos account. I just did the sign in with Google because then it signed in with my St. Paul account, and I highly recommend doing that. No, I don't have do that. I don't recommend it. You have to do it because otherwise, when you go away from your graph, it'll be gone forever, and that's really frustrating. So I have made this template for you to make it really easy for you to graph your results and start to get a feel for what they mean. You can see that I've labeled our axes here. We have mass on the x-axis and stretch on the y-axis. So mass is our independent variable. We're going to plot it on the x-axis. In general, independent variables go on the x-axis. If there's time involved, then you always put time on the x-axis, but I'm not that picky. I'll just let you know if they're wrong and you'll switch them around. It'll be fine. I do want to let you know you can change the axes labels by clicking on the graph settings, and the labels are here. You can change their ranges, which is nice, and their step sizes. There's a lot of different options. It's very convenient. Desmos is great. So then I have a data table for you here. So you see it says M1, so these are going to be our masses. I would like these masses to be in grams, so you need to have calculated from number of pennies to grams. And then we're going to have our stretch in centimeters. And again, this should be the stretch of your rubber band, not the length. So you'll type in your data here. And actually, I'm going to go ahead and pause and I'm going to type some random numbers. Okay, so I've quote unquote entered my data. I just made these numbers up. Your numbers will not be the same as these numbers, but I've entered in my data. And if your range here is a little bit uncomfortable for your data, probably your rubber band only stretched 10 centimeters. You can go ahead and change it. You can zoom in and out with your fingers. When you upload the picture of your data at the end of this, you will need to set it to a specific range of values so that everybody's data can be compared really easily. Okay, so then what you want to do is set your error bars. And so we're going to determine how large each error bar should be for the x and y variables by using the largest of our measurement uncertainty or statistical uncertainty for each slider below. So our horizontal uncertainty box, the horizontal uncertainty, horizontal is this way, is going to be for the mass. And this is that uncertainty amount that we decided in class on Monday. I'll have a little post-it note about it, a little page about it from what we decide, because pennies are a mystery. But we will have some measurement uncertainty for pennies, and I'm going to go crazy and say that pennies measurement uncertainty is 2 grams. Whoa, 2 grams of measurement uncertainty. And so you maybe notice that, and actually that's not that crazy really. Let's go even crazier. 4 grams? No, I'm going to change my slider size. I'm going to go all the way up to 10. And we'll do steps by 0.2, sure. We'll go really crazy. We'll go 10 grams because there's multiple pennies. We'll be talking about it on Monday. So then I need to figure out, well, what about my vertical uncertainty? Vertical is the stretch, and that's where you're going to need to look at your data table and say, okay, my measurement uncertainty for using the ruler was this much. Probably was a little bit bigger than the limit of the instrument. The limit of the instrument for the ruler would be half its smallest increment, twice that is the usual measurement uncertainty. I had a hard time reading my ruler and reading exactly where the rubber band was. So I would say it's probably going to be larger than 0.1. So that would be 1 millimeter or 0.1 centimeters. You can kind of decide, again, so long as you can justify the decision you are making with the way that you collected your data, that decision is valid. It should have probably one significant figure though. So I set my error bars for the vertical uncertainty box, for my stretch, and then I go ahead and keep scrolling. And now we're going to come up with a line of best fit. So when you're looking at data in science, you want to come up with the line of best fit that matches the data you have and is the simplest thing that matches the data you have. So currently, none of these, nothing. My data, I just made it up. So it doesn't have a great fit going on here. But what I have for you here are the different mathematical fits. So we have proportional, which is y equals ax. A is a proportionality constant. Linear, which you're probably familiar with from math class, is y equals mx plus b, but I'm using, again, a instead of our traditional m for the slope, because it's a proportionality constant that can exist in many different mathematical fits. We have an inverse relationship here, which is y equals a over x. And we have a quadratic, which again, you'll probably recall from math class here. So what I love about Desmos is that I have set up this template so that you have a little slider here, and you can just drag the slider along and change your values to see each graph. Okay, so I just fiddled around with the slider again because I noticed something interesting that caused me panic, thinking, oh my gosh, maybe I did it wrong, but I didn't do it wrong. There's something interesting happening here. So as I increase the slider, I'm changing the a value. And again, the a value is part of these equations. And so we can see the equations being graphed here on our Desmos graph. Again, you've probably seen this in math class. But I originally was like, oh my gosh, where'd all my graphs go? Where'd all my best fit lines go? But what I realized is that for us to be able to see all of these, they are at very different scales. So I have changed my slider. I'll change it on the template to something that'll work well for you. But what I notice is that if I have a very large value of a, you can see this green line. Because it's green, that means it's the inverse one. If I have a very small value of a, 0.001, we can see this quadratic line really nicely. If I make it a little bit less small, a little bit larger, we can see the linear, and actually that also includes the proportional line really well. You can uncheck lines just by clicking on them, so they stop showing up then. It's nice when you are just setting up your graph to kind of have all of these available and then be able to rule some out and say, oh, well, that like totally doesn't fit my data, so I'm going to unclick it. Or, oh, that doesn't fit my data, I'm not unclick it and not worry about it. There is also a slider for the y-intercept to add another level of complexity to figuring out our best fit line here. Notice that only linear has a y-intercept here, and that's okay. You can have y-intercepts in other relationships as well, but we're keeping things a little bit simple. And then I'll point out that there's a couple things down here that you're not going to mess around with. So in the future, I'll have a template for you where you can change what the variables are so that if we're doing a lab where you're getting to pick out what your lab is about, you're able to decide what those variables are and set them up. That's what this little area is for. And then this not for editing section is how Desmos creates the error bars. And if you're a fan of computer programming or you're just kind of curious, you can like look at these and click on them if you want to, but if you break them, you'll need to make a new copy because they're kind of challenging to fix. Okay, so that is our graphed template here. And again, your ultimate goal by the end of this week, week 5, is to have your graph with error bars that make sense, that you can justify and be like, Ms. Getz, this is why I said that. And then I'll be like, oh yeah, you have a justification for it, I buy it. And a line of fit that seems reasonable to you. I'm going to give you some leeway on how you do that line of fit. Next week on Monday, we'll talk about min-max lines of fit and how we're going to be approaching those in distance learning and how that might be a little bit different in real life school and return to learning. Hope this made sense. When you have your graph the way you want it, click save so that it saves. And let me know if you have any questions or run into any challenges.